Hi, welcome to my Lab 5, which is obviously the Choose Your Own Adventure lab. And for this lab, I have chosen to, well, for my adventure, predict solar orbits. To do this, I have used several fundamental principles. Obviously, the first of which is Newton's second law, that dt is equal to F net. Newton's third law is also relevant here because the sun doesn't just exert force on the Earth. The Earth exerts obviously much smaller but still statistically significant force on the sun. And finally, sorry, my lungs are feeling so good right now. We have Newton's law of universal gravitation, not gravitation, which is obviously what we're going to be using to calculate F net. And then obviously there's some data here which is largely acquired from reliable sources on Google. So to move on to the code that I've used to model this, we have our initial conditions, so some of these here aren't important. Like some of this is visualization, which is not important data, like the radius of some of these visualizations. But what is quite significant is obviously our definition of G, our time definitions. And for each celestial object, there's like a block of code, as you see here, with its initial position and an initial velocity and other such things, and its name. And now what we do with this is obviously we do a calculation loop where for every object, we go through and we look at every other object and we find the force exerted on every object by every other object. So, for instance, if we're taking the Earth, we look at the Earth, and we say what force is exerted on the Earth by all the other celestial objects in the solar system, not including the Earth, of course, because it would not make a certain degree of sense for this model. And then we calculate based on that F net that we calculate using NLUG, Newton's universal law of gravitation. We calculate using Newton's second law the effect this should have on the velocity. And we do this until the time cap runs out, which takes a certain amount of time. And before I show you the data results here and compare them to the actual correct results and explain what I think this means, I'd like to show you the visualization. So I did two visualizations here. One is zoomed into the inner planets with a slightly slower loop rate, so you can see what's going on in the inner planets. And one for the outer planets because they take significantly longer to make their orbit paths. And obviously you see with the inner planets, the visualization is obviously not accurate, but their orbit paths are there, and then you see the outer planets with their much slower gas giant trajectories. And Pluto is not a planet. So what are the results here and what do they mean? So as you can see, the first ones have a reasonable degree of accuracy. Mercury is our system predicts 90 days, and in fact, Mercury's orbit time is around 88 days. Venus, we predict 224, and Venus's actual is 225, 370 to 365.25. But we notice as we get further and further away from the sun, we start to experience more and more inaccuracies. And I'd like to discuss why I think this is. So first, I think part of the problem is that the data is not perfect, right? So we have modeled all of these planets as starting in a very long row. And that's not accurate. The planets don't start in a very long row, and that will influence their orbit paths, because obviously as our system is taking into account the orbits of planets is determined by not just the sun, but all of the other, not significantly, but it does change the trajectory slightly, all of the other masses in the solar system. And then also I think we experience some inaccuracy with Earth and with the moon because we're not taking into account, the Earth and Mars, because we're not taking into account their satellites. The moon does to a certain extent exert some force on the Earth and vice versa, which will influence its orbit path. But again, I think a big part of the inaccuracy here is because we have all the planets lined up at the start. But given that all we've essentially done here is line up a bunch of planets, give them a roughly accurate mass and initial velocity, a roughly accurate distance from the sun, and set them going using Newton's fundamental principles. The data we achieve just modeling is incredibly accurate. That's a real testimony to physics. So what do I think we've learned from this lab is that, well, I'm running out of time, is the importance of taking into account it's not just the masses and the velocities and the positions in the solar system, or the distances in the solar system, but if we're going to model it even more accurately, we need to take into account moons, such as Io and Apollo and some of the more massive moons. And also we need to take into account the initial positions of all of our different celestial objects. Because, if Mercury and Venus start aligned with each other, right, as though there's kind of a total solar system-wide eclipse, that is not going to be the same as if they started in different positions. And moons, although not that massive, do influence orbit paths. And then finally, I think the last thing that we can consider here, and I'm out of time, but I'll just say this anyway because I think it's interesting, is that the solar system, there are other stars, and although they're very, very far away, and the solar system is not static, right? All of these bodies are also moving in other ways due to other, massive dark matter and gravitational forces that I'm not even going to attempt to try and model, but they're fascinating. So in summary, that's my lab 5, and I'd just like to switch tabs and show you the code, because obviously I had a lot of fun writing this with the help of Dr. Alsea, and I think it's very fun to watch and look at. I think you could do some really fun things here modeling, and if you project an asteroid in and see if you can get it to hit the Earth. Obviously that wouldn't be good, but I think you'll find when you do that Jupiter will say no most of the time, which will be very, very fun. Anyway, all right, thank you for listening.